Hello. Hello, people of the r2con. How are you? Are you having fun? Not yet? I'm having fun. So I came here last year, had a good time. It was kind of my introduction to R2. I haven't really been using it much, even though I've been reverse engineering for possibly like 10 years or so. Mostly focused on malware. But yeah, came, had a good time, and then I've played with it, had a lot of fun this year. And I'm here to talk about a plugin that I'm currently working on, which I call zdbg, for no good reason, really. So what it's trying to do is to turn R2 into a stealthy kernel-mode debugger. So I do depend a lot on debuggers when I analyze malware. And user mode debuggers are fine in some cases. But if you're dealing with like rootkit stuff that operate in a kernel, then obviously you need a kernel mode debugger. Or perhaps even more common, a more common problem would be that the malware typically spawns multiple processes and injects code everywhere. So you sort of, need to handle it a little bit differently. So I call this thing a hypervisor debugger. I'm not sure if that's a good name for it. It's sort of similar to what you do if you do like remote kernel mode debugging using Winbag-ish, but not quite. So I have this illustration of my system, what I'm trying to do. Obviously you have your R2 with all of the cool stuff going on. And you might know R2 has an IO abstraction layer, which means that you can write plugins for it, so that you can basically write a debugger backend, so that whenever you type your command to single step or whatever, the plugin will actually do the work for you. And similarly for reading and writing to memory, obviously. So that's on this side. On the other side, I have my Windows VM. Since I'm working with malware, I tend to work a lot with virtual machines. It keeps them from spreading, and it makes my life easier. And then I'm running QEMU with KVM. It's basically for the virtualization solution. So what differs between like this approach and like a regular WinDebug approach is that we're not really, there's no debug mechanism inside the Windows guest itself. So everything happens on the host. Okay, so I'm running a Linux system, targeting Windows, and I had this idea of using an ancient protocol called GDB Remote Serial Protocol, which is something that is supported by most of the virtualization software out there, like QEMU, VMware, others. And it enables you to basically control the hypervisor in a way, I suppose. You can stop the CPU, start it, has a lot of stuff. But it also has some limitations that I had to get around. So let's talk a little bit about the ancient monstrosity. By the way, I think Defragger, did you write this? If you're here, thank you. I believe it was. So thanks. It's nice to not having to, do this myself. Actually, I didn't really have to modify this code much at all. Just minor things here and there in order to make it work. So basically, Radar will be the GDB client. QEMU would be the GDB server, so that whenever you want to say, please single step the CPU, you would just send a packet, which is actually just the ASCII S. QEMU will say, okay, I'll single step the CPU, send you like an OK packet back, or if there's an error, it would tell you. So that part of it works quite well. So the second thing you need to do is you need to grab some registers, whatever the instruction pointer changes, you need to know, obviously. Which is okay-ish. The only thing is that in order for me to do what I'm trying to do, I need the values of more registers that are currently supported by GDB. I suppose GDB is sort of made to be a user mode debugger, and there's a lot of registers, and I'll get to that in a second. But I need to know the value of in order to do what I'm trying to do. So the third aspect of this is how GDB is meant to read and modify memory. So there's two main problems with this. First thing is that you're actually transferring potentially large amounts of data over the network. Even though in my setting I'm on the same machine, I'm on the Linux host, and it's running the Windows VM, so there's not really a good reason. I mean, in the old days when we actually did proper remote debugging with 2 machines, then the only way you can transfer the memory contents would be via the network, but it tends to be quite slow. The other problem I have with it is that it's designed to read a virtual address. And as I'm sure you all know, the virtual address, the contents of whatever is at the virtual address will change depending on which process you're in. So if I want to debug every single process, then that becomes a problem. So what I suggest to do is just to throw that out entirely. And a good colleague of mine came up with this. He did some similar hacking on QEMU, and he came up with this quite brilliant idea of sharing the guest's physical memory with the host. So the way this works is like internally, whenever, say you have a Windows VM with 2 gigabytes of RAM, internally QEMU has to allocate memory for this. So it's basically a malloc of 2 gigabytes, and then that becomes like the buffer that Windows is using for its physical RAM. So I mean, long story short, if you, instead of doing malloc, you do an mmap, and just like share that with the host, then this becomes much quicker, and it means that basically the R2 process will share memory with the QEMU process via my plugin. So that's what I'm using for reading and writing to memory, and then I'm using the zdbg protocol for like debug control kind of things. So I need to sit for my demos. This is not how I normally work. Okay, let's see if we can do this. See if it works. So yes, can you see this? So I have my Windows VM running here. It's Windows 10. It's currently what I'm focusing on. I do support some other older ones as well, but Windows 10 is more interesting. So you give it like 64-bit debug, and then I have this is the file where QEMU has shared the guest's physical memory, and prefix that with zdbug, and boom, you can see. Yeah, you can see, hopefully. You can see that there's sort of like 2 I/O channels. First of all, the first one is basically the shared memory thing, where it's connected directly to the guest's physical memory. And the other one is the zdbg stuff on localhost, which is basically QEMU listening on localhost 1, 2, 3, 4. So you can see I print like the current thread and the current process ID. One of the challenges with doing this is that you don't really control where you end up. So basically, whatever is running on the CPU will end up just being frozen. Okay, so you just like stop whatever is running there. If you're using WinBag, there's like a safe haven. You land in on an int3 instruction. You can just see this is frozen. So it is random, but very, very often you will end up here in this place, just following a halt instruction. So if you want to know where you are, you have your DMM command, which would, in this case, list all of the running drivers on the system. If you want to know where you are right now, basically you do this. You add a dot at the end of it to tell you, okay, so I'm in this hardware abstraction layer. At this point, it's kind of helpful to load some symbols, so I'll do that. All the symbols, which I've already downloaded using R2, actually. So let's load the symbols for HAL, PDB. Has a bit of an extra output, so let's pipe that. And while we're at it, we might as well load the symbols for the kernel, because we need them. Base. This is horrible to type. MP, I think. Yeah. Goodie. Okay, so back. So it might be a bit easier to read. You see that we're in the something called the processor idle thingy. Okay, so we're in the idle thread, and we're basically debugging the idle thread. That's what I've been doing for the last few weeks. Very fun. Okay. So in here we can obviously it works like a normal what you would expect. So you can single step out for a little bit. You can figure out where you are just running the DMM command again. Okay, so it's in the kernel. You can single step some more. You can step over if you don't really. I don't really care what. Oh, actually, I know what this does. So I'm not interested. You know, you can place your breakpoints. You can go. So yeah. Also, you can inspect like the other processes running on the system. So this was the dp command, which will list all of the running processes. And then you can select them. Basically what I do is, oh by the way, I guess I should say this. This is like a special command that means that I'm sending commands directly to my plugin via our IO system thing. So it's just like a callback I implement in my plugin. So I operate with like two kind of targets. One is live. It's the one that's running on the CPU. And target is the one that you are currently inspecting. So what you can do, even though like the idle thread is running, say you wanted to have a look at Explorer, you would just select it like this, give it the PID, and type that correctly. And then things change a little bit. So if you do the DMM command now, this is the way I've made it now, I'm not sure if I might change it, but basically it would give you the loaded DLLs of Explorer exe instead of the loaded drivers. You can see there's quite a few, and obviously you can inspect all of this stuff if you wanted to. This is the loaded base of Explorer. This is I'm just printing the entry point because I found that nice to have. So yeah, you can snoop around in the other processes as well. Yeah, let's get back to some more slides. Yeah? So I wanted to talk a little bit about memory translation. I'll try to skip some of the details, but it was sort of a large part of what I had to do, and it turned out to be a little bit more difficult than I was hoping for. But I'm still alive. I think at some point I did consider killing myself, but it was okay eventually. So how this works basically on x86 is that you have a virtual address and you're looking for a page in memory. So everything in physical memory is organized as a page. Typically it's like 4K in size. And you have the value of the CR3 register, which is one of the registers that GDP does not normally include, but one that I really need. And the idea with this is that the CR3 register will point to the directory base table, which is sort of like the first table of this lookup process. So whenever you change a process in Windows or possibly other operating systems as well, the value of CR3 changes. So basically every process has its own CR3 value. And then from the virtual address you extract some indexes into these tables, and for each of the table they will give you a pointer to a new table. Do that 4 times, more or less. It's a bit simplified, but yes. And then you end up with something called a page table entry, which may or may not be valid. But if it is, then the last part of the virtual address will basically give you the offset into the page, and so you will find the contents that you want to read or write. Yes. This wasn't too hard. I mean, I did get it wrong a couple of times, but yes. It wasn't too hard. The thing is that even though it's invalid, all hope is not lost. But one thing that I want to point out is basically for every read, I need to do 4 physical reads to do the translation process at the minimum, and then I need to do the fifth read. So I guess that's why this is normally implemented at hardware, because it's such a huge overhead. Yes. What happens if it's not valid? And this is sort of where Intel and AMD stops and Windows begins. You see, there's like the least significant bit is the thing that indicates whether or not the PTE is valid or not. If it's valid, then you just take some bytes in there and all them together, and you find the page. Basically, it gives you the page directly. The thing is, if it's invalid, then the hardware won't touch it at all normally. So this leaves actually 63 bits for the operating system to use as it sees fit. And Windows is using this internally in basically the memory manager. So what happens is if the PTE is invalid, hardware will issue a page fault, kernel will catch it, and it will try to figure out what to do. So I mean, the most obvious thing is that it's actually been swapped out or paged out to disk, which can happen. In that case, like there are bits in there that will tell you the location of the page file and the offset in the page file, so that the memory manager can go and grab and page that contents back in. There's a concept of demand zeros, which means I don't really care, just give me a 4K of zeros. It's a funny thing that it can be in transition, which is somewhere in between the swap file or the page file and in memory. For us, it's quite simple because it actually means that it is a valid PT, so we get it directly. But it's probably some implementation in the Windows memory manager that I'm not aware of. But yeah. And finally, the hardest one is that it says, I don't really know, go and search something called the virtual address descriptors, which is slightly more annoying. So in order to do that, we need to grab some very important structures that the Windows keeps in memory. And I talked about some of the registers that were missing from GDB, and these are some more. If you've ever seen like shell code and stuff for Windows, you'll probably be familiar with like FS30. No? Okay. Quite typical. They're parsing something in something called a thread environment block in user mode in order to basically figure out where the DLLs are loaded and find the address of a function to call, for instance. And there's a kind of a similar concept in the kernel called the kernel processor control region, which all of these basically have a base address in special registers on the CPU. And since both the user mode component is using GS as well as the kernel, then those two will be different. And whenever you have a transition from user mode to kernel mode, the kernel will call the swap GS instruction, which I guess I can just show you. Since we have the symbols in red, we can go to this guy. It's called system, something like that. This is basically the routine that is being called whenever you do a syscall from userlad. So the kernel has basically registered the address of this function beforehand. And you can see the very first thing it does is like a swap GS. Just because it's coming from user mode and GS points to this tab thingy, and the kernel needs it to point to the KPCR thingy. And afterwards you can see it's referencing GS. Firstly, it's saving the user mode stack pointer, retrieving its own stack pointer, setting up something called a trap frame on the stack. It's not very important. And there the 188 one is grabbing the current thread, for instance. So this is sort of something similar that we need to do in the plugin. And we can do it as long as you know the value of GS base, or kernel GS base, and you have some knowledge. Obviously, you have the symbols in Windows, so it's not impossible. It's just a bit painful sometimes. What this ends up being is from the GS, you can grab the kernel processor control region thingy. From that, you can get an E thread. From that, you can have a process, and each of the process on the system will basically have something called a VAD root, a virtual address descriptor thingy, which you can see quite clearly is a red black tree. quite happy with this illustration. So, what does this mean? Basically, this tree will describe all of the virtual addresses belonging to a certain process. So think of a node in this tree as like a DLL that has been loaded. It's quite often what it is. So what we need to do is basically traverse this tree, as we have our target virtual address, and then you just walk left or right depending on if it's too low, too high. Hopefully you find a match. From there you can access basically one of many prototypes PTEs, which is something that Windows dreamt up as well. Basically, you can say like typically one DLL would typically span multiple physical pages, and for each of those pages there would be like a prototype PTE thing, which you can grab. So and then the final step is figuring out what on earth is a prototype PTE. Well, that can be different things as well, of course. Actually, it can be either it's actually valid, so you will actually find a way to locate the page immediately, or it can actually be a prototype, which is prototype bit set. This is, I don't know why they made it this way, in which case they've just encoded the PTE in there somehow, so you just need to flip some bits around to extract it, then grab the page, or it can be a pointer to a prototype PTE. And this is where I was becoming suicidal, because some of my translation, I mean, it didn't work, and I was like, why? Oh yeah, it's not, I mean, the details aren't really important. I just wanted to share some of my frustration with going through this, and thankfully I'm still alive. So the good thing is that once we've done all this, parsed all of the tree structure, we know how to walk it. There's a lot of other information in the VADs. Such as like the protection stuff, the tag stuff. If anyone has ever coded drivers for Windows, you might have used like ex allocate pool with tag in order to allocate memory, which is where you pass in a little tag. That's that tag. Has your array of prototypes PTEs. It has like the file object thingy, which includes more details I didn't want to put on the slide. And finally, it has something called a linked list of subsections, which is sort of more of a granular, like more detailed view of the layout. Oh, okay, so I'm coming to this slide finally. So I can use this in order to get the memory map of the process. It's basically the same tree, and instead of searching through it, I'm recursively walking it. So I'm finding every single node belonging to this process, and from all of those nodes I extract information such as, I mean, the range of it, the protection of it, and then if it has any subsections, you can get a more detailed view. And that's how I implement dm command. So, okay. Let's detach it for a little while. Some stuff was paged out. It's still a problem for me that it's paged out. Detach it, break it. Nah. Let's take another process then. Let's do something you know. So I can type. Okay, so this is the memory map of the Radar 2 executable running in Windows from Linux. Bit of overkill. Well, you can basically, what I meant to see with the like the more granularity thingy is typically this. So the header will have like a read access, read execute, read write. So all of these are typically subsections. Okay. At least we have the memory maps. Yes. Let's see. How am I doing on time, by the way? Is anyone keeping track?
We're doing okay, Matt.
So how much longer do I have? Okay, now I just include everything. Okay. Next little hurdle. There is another structure in memory that is quite important to us. It's used by WinBag, like debugger, Windows debugger. It's used if there's a crash dump. For instance, if you've ever seen a crash dump on Windows, it typically includes information such as like which driver was responsible for doing this stupid thing. So the kernel needs to keep this information somewhere, what's loaded in memory. The problem is that even though you can get the offsets from GS base, again, GS is like the super important register, and it has this one pointer to paradise in kernel. So as long as you know it, you can read the symbols, you can get the offset from it, but still it's encoded. I don't think they did this in order because they hate me, or maybe. But I think it's mostly about the fact that actually the base address of the kernel is in there. So if it's in clear text, then there might be problems with info leaks and kind of thing. If you're doing bad things on Windows, you might want to read the structure at some point, I'm guessing. So what I did for this is a cool thing about coding with R2, because you can sort of use the framework as you're developing stuff, which I find funny. You can break it, yes. Yeah. Beep beep. There is a function. Because I told you that the kernel is making use of it. And this typically means that at some point the kernel might need to decode it itself. So if you figure out where this is, or where this is happening, you can reverse engineer it. I mean, why not? So you see, this is a routine to copy the data block. I'm assuming it's being used to copy the encoded thing into some other buffer. Or actually, I know that's the case. So you can see it's checking whether or not it's encoded. Again, it's nice to have symbols. It will take this right branch if it is. We'll set the size of this thing, basically the entire block. It wants to decode, and it will go into this loop, which sort of the way I read this in my mind is it has sort of 3 inputs. It's referencing a value which has a kind of a weird name, I wait never. And it's using the address of this, presumably a Boolean value indicating whether or not it's encoded. And it's using the value of something called I wait always. So these symbol names are meant to not, I mean, they're not, there's a reason why they're called this, basically because Windows don't really want you to know what it is, I guess. But if you see the code, you can see that it's kind of a typical obfuscation thing going on. You have an XOR, rotate left, XOR, byte swap, and an XOR. So just flipping bits around to be annoying. But if you know the algorithm, then you can just re-implement it. So this is the code basically that I lifted from this routine. And you can see the same thing. I mean, yeah, basically the XOR rotate left, and those 2 lines under the initial XOR, another XOR, a byte swap, and an XOR. It's not super, I mean, it's not that hard. Maybe I didn't get it right the first time either, but it was, yeah. But one of the, I mean, kind of like an interesting thing, before this conference, I sort of did some Googling just to make sure that, yeah, just to make sure that I'm not saying too many stupid things. And I came across this article in the magazine called Uninformed, which I read a long time ago, by this guy called Skywing, which was basically reverse engineering PatchGuard on Windows. And he came up with they introduced this new obfuscation thing in 2007. It's basically doing exactly the same thing as I'm doing. So if you look at this code, it's like there's an XOR, there's a rotate left, there's an XOR, there's a byte swap, there's an XOR. So apparently Windows has kept this obfuscation algorithm for, I don't know, 10 years. Still using it, even though, yeah. I don't know, I found that funny for some reason. Maybe I don't have the best humor. Could be. Okay. Do you have time for a final demo, or should we stop? Okay. I'll try. This is sort of where I'm at. I told you I'm not quite done yet. Needed more time. Basically, some of the stuff I'm struggling with has to do with breakpoints. So if you see how the GDB protocol works, or is intended to work, I guess I even told you, is that basically the client, which would be us in this case, we're supposed to request that the server places a breakpoint somewhere. Okay, so it's not, we are not writing the CC, it's QEMU in this case that we're supposed to write the CC byte and also remember what it replaced it with. And the problem is, as I told you, all of this this translation madness and all of the pain I had to go through to get it right. The thing is, like, QEMU is doing the same thing, but it's not doing the extra thingy that happened when the PTE was invalid. So as long as the translation process actually translates into something useful, this works. But there are some cases where it doesn't. And basically what I'm saying is QEMU does not really know about all these structures that Windows is keeping in memory. So I'll try to do like one last demo. Let's see. So if I select Explorer, let's see where I am. Yes. So I call this like a concept of remote breakpoints, because basically what happens is right now the idle thread is running on the CPU, and I want to place a breakpoint inside Explorer exe. So I'll give you guys a question. How would you do that? So the trick is that QEMU doesn't know that I want to place it on Explorer exe, and if you don't do anything, it will typically just, it will resolve to the value of, basically we'll use the value of CR3 belonging to the system process or the idle thread, okay? So I have a little trick, since I know the value of CR3 for all of the processes, so I just like temporarily write the new value to CR3 and instruct QEMU, go do your stuff, please, try your best, and I'll write it back. That's a fun little detail. Yes. So let's say we wanted to, I don't know, place a breakpoint at the entry point of Explorer. Possibly not the, yeah. Let's do it here. Let's place it here. So you can see the call instruction. And I have a, so just again to remind you, I put the target as Explorer, and I have some special command as a remote breakpoint. Oops. Copy pasting is hard. Okay, boom. So you can see it's actually writing a CC into that. A QEMU is doing it. It's not fully integrated into R2 yet, so I mean normally this will be hidden. Maybe that's why R2 will just show you the B. But at least it works, as long as the memory translation works. So let's try an example where this doesn't work. And this is a demo that I don't know, I might get kicked out of r2con for doing this demo. Don't throw things. I thought it might be funny. Anyway, let's say we wanted to debug a new process, one that is not currently running on the system. So if I wanted to place like a remote breakpoint into it, the problem is that basically it doesn't show up on my list. I don't know the PID of it. Quite frankly, right now it doesn't even exist. But I did find an interesting place in the kernel. It's all about being clever. Actually, let's do this. Seek. Okay, so this is a routine that is being called as part of the process creation thing. And it has an interesting function called insert object. We place a breakpoint just after that one. Continue. I'll just ignore that for now. Funny thing is, and this is the part that might get me kicked out. Sorry. I'm starting a new process. Okay, and then it froze. Okay, the entire thing froze. This is why I heard some rumors that Pancake had put some IDS alarms and something that the fire alarm would go off if you ran this. Sure if that's true. Okay, then let's see. Yeah, we broke where I wanted to break. Does that make sense? We ended up where I wanted us to end up. Funny thing is, the process creation isn't really done, but it's gone far enough that this program shows up in the process list. So we can select it. Okay? And now you can see that if I do like a DMM, there's actually no modules loaded yet. It goes pretty quite early in the loading process. But there should be some VADs, so you can still do like a DM, and you will see some program loaded here. So let's say we wanted to start debugging from its entry point. You can do this is the base address of it, something like that. Yeah, so my point was, if I wanted to place a remote breakpoint there, it should fail because the translation process doesn't work out for QEMU. Why am I? Hard. Okay, so if we go there, we should not see a breakpoint. But we can still write to it. So that one of the things that I'm considering doing is to just implement the breakpoint thing myself, because since we are so smart, we can place like an alternative to a breakpoint. So make a note of the original byte. I'm about to patch it. So we do basically a write X EBFE, which would be an infinite loop. If I did that, oh, right X infinite loop. Yes, Let's make sure I don't have any breakpoints. Go. And you can see it's really struggling. It'll break it. And we're in either. If you go to, so we sort of managed to get there the hard way. And since we can be nice to either, we can patch it back. What was it? EB. Right. E86E maybe. Okay. Worst thing is other crosses. I don't know. Okay. So from here. Okay. So you can single step it. There's one thing to point out though. Minor annoyance. You can see that since IDA is a 32-bit app running on 32-bit program running on 64-bit Windows, I normally have to do this just to get the disassembly right. Okay. So we can debug it or just let it go, and it should pop up. And don't throw things at me. Okay, that's it. Thank you.
Any question?
Hey, so I was just wondering if you had to implement yourself working the process tree, because you have some nice commands to show the processes that are running on Windows.
Yeah.
So did you have to look yourself the kernel structures to iterate over the processes to do that?
Yeah.
Or, okay. So,
so basically, what you can do is, if you have access to the kernel itself, I don't have an internet connection, but basically, so anti-OS kernel, right? What you do is type this command, pp, and just give it the name, and R2 will actually go and download the symbol files for you, which will be this guy called anti-kernel mp. And then you can basically do like rub into p and t. Pipe that to like symbols, text, and you have like all of the symbols.
right, but
It's got a few symbols, but yes, you can do it.
But those are just symbols, right?
Yeah. There are symbols, but I mean,
So is there like a Windows API you call to?
No.
So you really dive into the
No, I just parse physical memory basically.
Yeah.
Yeah, obviously, if you're running on Windows itself and you wanted to do something similar, you would call an API somewhere, or like call some function. But yes, you're basically just parsing the raw structures and retrieving it. Actually, I want to say one more thing, because I want to thank some guys. I was so deep in my demo that I forgot. So I'd like to give some special. First of all, my entire team in Symantec Norway, especially Stian Myhre for doing his word trick with the QEMU share memory thingy, and Bahan Amne for just bothering to sit down with me and discuss Windows internals all day long, and for R2 and Pancake, obviously. I just saw like the names of most of the files of the code that I've had the pleasure of reading. Defragger for GDB stuff, Lemon Man for WinBug, because it was one of those. I had great help in reading some of this code in the start of my project, because I didn't know how to write a R2 plugin, so I needed to figure it out. And Insider for the PDB stuff, and anyone else who has ever contributed. I love you guys. It's amazing. Thanks.